Hey everybody, welcome back. Today, what we're going to cover is kind of like an extra topic. It's not, you won't find this material in the textbook, and there isn't really a textbook that I necessarily pulled this material from. It was a little bit pulled from here and there because it's meant to be a very quick um, and sort of fast and loose introduction to the Fourier series and the Fourier Transform. But this is nonetheless a very, very important uh, concept and idea in both numerical analysis and signal processing. Um, and so I thought that it would be might be useful for you to have been exposed to this idea at least once in your undergraduate engineering coursework. So we're kind of returning to this idea actually because I had mentioned a couple of lectures ago when we did modified wave number analysis for stability that because we made an ansatz or a guess, right, for that wave number analysis that was justified by the fact that you could express functions as sums of complex exponentials, right? Well, those sums or series are called Fourier series, and so the sort of hallmark here. Let me make sure I start recording here. Okay, and so the Fourier series statement is the following, which is that any function that is in a space called L2 from 0 to t. Okay, that's an L2 function. But what that means in math actually is the following, which is that the integral from 0 to t of the modulus of f of t squared. So if f of t is a fully real function, it's just the absolute value squared. But if it can be complex valued, so it's the modulus squared dt. If that integral is less than infinity, then that function is in L2. Okay, so that's the definition of L2. Just kind of like link these two together by highlighting both of them. So that's any function that satisfies that rule is an L2 function. Okay. Can be written in the following way. Can be written as the following. F of t is equal to the sum from n equals minus infinity to n equals infinity. Okay, so like over all integer values of n. Should just put infinity on the top there, not n equals infinity. And the terms in the sum are some coefficient that depends on the index, Cn, times e to the 2 pi n, the imaginary unit I, t, divided by capital T. Okay? And those coefficients can be calculated in the following way. Cn is equal to 1 over t times the integral from 0 to t of e to the minus 2 pi imaginary unit I n t over t times f of t dt. Okay? So just to make it very clear, this is a sum over all n in this space called Z. That's just positive and negative integers. Okay? And since that is the case, we also have with the form of Cn here, if we take that sum and the fact that Cn is in that form, if you plug in a negative n to that formula for Cn, it just changes the sign of the constant that's attached to the imaginary unit I, right? Which is the same as taking the complex conjugate. So that means that C minus n is equal to Cn star, which is the complex conjugate. Remember, the way you calculate a complex conjugate is you find wherever I is in the expression and you multiply it with -1. And that also means, or implies, that the magnitude of Cn, or the complex modulus of Cn, is equal to the complex modulus of C minus n. Okay? So, in other words, when you calculate the CNs, they're kind of mirrored about n equals 0. And you can also break up Cn in a specific way that allows you to write everything in terms of sines and cosines. Because remember, a complex exponential via Euler's formula can be written as sines and cosines. So if we express Cn as the following, where we have 1/2 an plus I bn for positive n, and 1/2 a absolute value of n plus I. Oh, sorry, this first line should have a minus sign here. An minus IBN. And this should be an plus IB absolute value of n for n less than 0. And then we have a naught over 2 for n equals 0. So if we structure Cn in that way, then we can express the Fourier series in terms of just trigonometric functions, which is like this. F of t is equal to a naught over 2 plus the sum from n equals 1 to infinity of a n cosine of 2 pi nt. I think that should be divided by t here. Plus the sum over n equals 1 to infinity of bn times sine of 2 pi nt over t. Okay, and that's like the trigonometric representation, or the trig function representation of the Fourier series. Okay, so just like Taylor series, this is like you can truncate after a certain number of terms and you end up with an approximation. But if you keep all infinite terms, this is a perfect representation of the function within that subinterval 0 to t. And because these are periodic functions, all of these functions are periodic with respect to the period capital T, then if you represent a function, this function in general is going outside of the interval, is just going to repeat forever. Okay, so really what we're doing is we're finding a representation of the periodic extension of f of t from 0 to 10 to capital T. So I'll kind of make that more clear as we move on through the lecture, what I mean by periodic extension and things like that, okay? So, in fact, I can even just draw it really quick. So, note finding representation of periodic extension of f of t in the interval 0 to t. So let me draw what I mean by that. So let's say we have a function that looks like this. This is f of t, and this is t on that axis, and then this is capital T. And we have that the function kind of comes in from the bottom here, and it goes up and down, and then over a little bit, and then heads off in that direction. Well, the periodic extension is going to essentially copy this exact behavior until it hits these boundaries, and then it needs to repeat. So it's going to jump up to wherever it was before, and it's going to go over and up. Whoops, sorry about that. Over and down. Let's try to draw this in a way that looks the same. Go up. It's kind of difficult to draw this one. My hand is almost blocking it. Then this drops down here to here. It goes up, down, up, and then over. And then that just repeats over and over and over again. So it goes down, and then up, and then this guy's going to go up, and then over. So the periodic extension, it's taking everything of the function values between 0 and t, and it's just copying and pasting them every capital T on the t-axis. Okay, hopefully that makes sense. That's what I mean by periodic extension. Okay. So that's the basic idea. But that's really just a statement of results. To motivate those results, or to at least explain a bit about where that comes from, I have to talk about the concept of orthogonality. In the context of functions. So you are probably familiar with orthogonality in the context of vectors or directions, right? So if two vectors are orthogonal, they have a 90-degree angle between them. But the definition of that in vector calculus really lies on this idea of taking the dot product between two vectors. So if you take the dot product between two vectors, you get 0 as your answer, right? And in R3, which is like kind of three-dimensional vector space, that looks like the vectors having a 90-degree angle between them. But the idea of orthogonality actually extends beyond that to any space where you have a defined inner product. Okay, so talking about what we were just saying, vector orthogonality uses the dot product as the so-called inner product. So that's a special kind of product that establishes a notion of distance in a set. Okay. And so what you end up with is the following, where you have something like x, which can be in R2 or a two-dimensional space, is a times E1 hat plus b times E2 hat. So E1 hat, to be clear, is like basically 1, 0, and then E2 would be 0, 1. Okay, just two-dimensional vectors. Let's say that y is equal to c E1 plus d E2, right? Well, x dot y is equal to ac plus bd, and then if that is equal to 0, then x is perpendicular to y, right? They're orthogonal. So in vector land, E1 and E2 form what's called, and this might be familiar for those of you who recently took a linear algebra course, they form an orthonormal basis. Orthonormal basis, which I will often abbreviate ONB, okay, for a space called R2, which, like I said, it's just the space of two-dimensional vectors with real coefficients, okay, like a two-dimensional space. Okay, so there's a couple of key ideas here. Key ideas. One, all vectors in R2 can be written as a linear combination of E1 and E2. And I'm hoping this is review, since linear algebra is a prerequisite of this for this course, as a linear combo of E1 and E2. Okay, so that's literally meaning, you can add these things together with different coefficients and you can form any vector in R2. That's what makes them a basis. Okay, that's the definition of a basis. And then 2, E1 hat and E2 hat are orthogonal to one another. Orthogonal to one another. Okay, which means, of course, E1 dot E2, which, if you look at what the vector elements are, would just be like 1 times 0 plus 0 times 1 is equal to 0. Okay, that's extremely critical. Okay, so that's what makes them an normal basis. So they're an orthogonal basis. And then also the normal part comes from the fact that E1 and E2 have norm 1. So like the magnitude of E1 or 2 is equal to 1. If you take the dot product of each of these itself, you just get 1. Okay, and so the idea is that we want to continue to extend this idea. So this up to this point, we're just talking about plane vectors and orthogonality. I'm hoping that for everybody, this is like, you're like, okay, this is a pretty basic review here. But what we're going to do is we're now going to think about, instead of vectors in space, we're going to think about functions as vectors in a vector space. Okay, so extend idea to functions. So, if you have two vectors, if you want to say how similar they are, you can talk about how, whether one has a much larger magnitude than the other, but really what matters for how similar they are is whether or not they're pointing in the same direction. And so if two vectors are pointing in the same direction, they're essentially the same vector. So you want to construct some sort of operation where you can take two functions, and if they're very close to one another, you get a bigger number, right? The dot product gets bigger, the inner product. And so it turns out that the complex exponentials, the complex exponential functions, which is like e to the I 2 pi n t over t, right? Where n is an integer using this funky notation, that n in z thing. Forms, or those complex exponentials form an orthonormal basis for L2, this function, that space that we came up with, right? That was basically saying if you integrate the magnitude of these functions over the space, you get a finite number. They're well-behaved functions in that way. So we actually get an orthonormal basis out of those complex exponentials. And it's a little bit more complicated, right? So like before we just had two elements that spanned R2. Now we have function space. It's like an infinite space, infinite dimensional space. So we need a lot of basis elements to span that space. Okay, so the inner product for L2 on the interval from 0 to 1, or 0 to t, I should say, is the following. It is written as f comma g. So that's like the way you would write general inner product, okay? And it is equal to the integral from 0 to t of f of t times g of t complex conjugate. Okay, so we're still working in the world of complex valued functions. Okay, and so now you can see why this becomes, you get the orthogonality here. So if we look at the dot product or the inner product between e to the I 2 pi nt over t multiplied by e to the I 2 pi mt over t, then we are going to get delta nm, which is defined as the following. So this is just, it's a little bit of notation again. It's equal to 1 if m is equal to n, and it's equal to 0 if m and n are different. Okay, and I don't know, maybe a lot of you aren't immediately familiar with this type of idea, but the idea is like, okay, let's just think about sines and cosines for a second. If you have two sines and cosine functions, one has this sort of period like this, right? And then the other one has, let's say, like 4 wiggles in the same space. Okay. If you integrate just one of these over a full period, any integer multiple of a full period, you're always going to get 0, right? Because the amount of area above the x-axis is going to be exactly balanced by the amount of area below the x-axis. Okay, so any sine cosine function that has, and I shouldn't even write the black one here this way. I should write the black one as like just having one full oscillation in this amount of time. Okay, and so if you're going over an integer number of periods, which we always are if we're going from 0 to t, the way that these complex exponentials are constructed, okay, because n is an integer that's in greater magnitude than 1, then you're always going to integrate to 0. And if you multiply those two things together, two functions that have different periods, you're just going to end up with something that also integrates to 0. Okay, this is just a rule about complex functions, because you're multiplying two things that spend equal amounts of time below and underneath the x-axis, and they're doing it on a different period in a different structure. Okay, so if they have a different frequency, but you're still integrating over an integer number of periods, then you're going to integrate to 0. But if the two indices are the same, then you're just multiplying the function by itself, and then this red line becomes, this now, and it's strictly positive for that integral. Okay, and then you'd just be integrating positive values, and so the integral becomes greater than 0. I think that, I don't know, maybe in the future, maybe when I deliver this lecture in person, I'll do a numerical example of this just so that you can see it. It's kind of hard to explain in words and in drawings. And I think that doing a strict mathematical proof actually wouldn't be too hard to do, because I think that you could do the trig integral relatively easily. That might not be trivial either. to do a general trig integral and show that it always is 0 if m and n. Definitely too hard to do off the cuff. So I won't try to do it here. But yeah, I'll try to improve this in the future. But if hopefully this little drawing made it relatively clear. But if it didn't, then you know, at least for the purposes of this moment, just take this for granted that this is true. And then you know, you can look for examples online for teach you how to do this, and on my end I'll try to make this better in the future. Okay, so this is like very much like the setup of an orthonormal basis, right? So you have these two, when you integrate these two functions against one another, or these two basis elements against one another, you get 1 if the indexes or indices are the same and 0 otherwise. That's like the same thing here, right? This is like points 2 and 3 on R2. Okay, and so we have all the components that we need to make an orthonormal basis. Now, sorry, this should be not 1 but t here. Apologies for that. So yes, that is t there, because this is, if you write out this integral, this is the integral from 0 to t of e to the I 2 pi n t over t times e to the minus I 2 pi m t over t dt, right? And that dot product, if m is equal to n, is just the integral of 1 from 0 to t, so of course it's going to add up to t, right? And so what we do for our Fourier series basis elements is we scale them. So scale to make them orthonormal or normalized. So en would be equal to 1. What that looks like is the following, where you have 1 over the square root of t times e to the I 2 pi n t over t dot product with 1 over the square root of t e to the I 2 pi m t over t. Okay? So, you know, in integral form, that's 1 over t, integral from 0 to t, just this guy here, right there, and that's going to be equal to t over t, which is equal to 1. Now it is literally equal to delta. This is now like t times delta is equal to delta. Actually, no, it's t over t, which is equal to 1. This should be n here. Apologies for the messiness there. But the idea is just to scale these complex exponentials so that it's actually an orthonormal basis. And they form a basis because, like we said before, the complex exponentials, we can write all of the functions in L2 as a sum of those complex exponentials. Okay? So we can actually, this actually shows by analogy how we can calculate the coefficients. So since these guys are an orthonormal basis, we can see by analogy how to, you know, come up with those formulas for calculate for the coefficient Cn. Okay, so in a vector, in vector land, where v is equal to, you know, v1 e1 hat plus v2 e2 hats, and so on. The way you write v1 or the way you can calculate v1 is by taking the overall vector v and performing the dot product of that with e1, right? That's going to, which you can also write as the inner product between v and e1, right? And that's of course just going to be equal to v1 because e1 is orthogonal to all the other elements in the sum. So for functions in L2 on the interval from 0 to 1, or 0 to t, I keep on saying 0 to 1 there, then the coefficient kn, where, so, you know, these functions can be written as sum from n equals minus infinity to infinity of cn e to the I 2 pi nt over t, and then cn itself is equal to kn over the square root of t. Okay? This extra sort of layer of arbitrary scaling is just to make this orthonormal basis reasoning work. The way you would calculate kn, which you can just divide by square root of t to get cn, is that you take the inner product of f of t with 1 over the square root of t e to the I 2 pi nt over t. Okay, one of the basis vectors, or the nth basis vector, more specifically, which is equal to 1 over the square root of t as the integral from 0 to t of f of t times the e to the minus I 2 pi t over 2 pi n t over t dt, right? And that's going to be equal to if we sub in this so that's the actual formula, right? But then we can also, you know, we know what the series representation is, and we can see that for f of t we can put in, you know, m equals minus infinity to infinity of km over delta t e to the I 2 pi mt over t. That's the full series representation that we know works via Fourier, and then that's multiplied by e to the I 2 pi nt over t. Okay, and we know just based on this sort of reasoning here that we're lifting out one from this infinite sum where all the rest are orthogonal. We're just going to get kn out. Okay, that's sort of your proof that this is how you calculate kn. Okay, hopefully I know that this is getting a little mathy, but it's okay. We're just gonna kind of push through this, make this jump over now to talk about the Fourier transform, and then at the end of this, I'll have some fun numerical examples to show you. Okay, so that's hopefully giving you a little bit of a brush of or at least a little bit of an understanding of what's going on with Fourier series. The next thing that I'd like to talk about is the Fourier transform, which is where we take this jump from the discrete sum world of the Fourier series and into the continuous world of the Fourier transform. So I'm just going to rewrite the Fourier series. So the Fourier series, and I'll leave out the kn's in the square roots sort of jargon for now. So the Fourier series for f on the interval 0 to t is f of t is equal to the sum over all n from negative infinity to n of cn e to the 2 pi int over t. And then those coefficients Cn are equal to 1 over t times the integral of 0 to t f of t e to the minus 2 pi int over t dt. Okay? So let's sort of notice something about this. So complex exponentials, remember, are just sine and cosines, right? So you can term this as that we are expressing, we express f of t as a sum of harmonics. Okay, so with frequencies, omega n equal to 2 pi n over t. Okay, so we could just sub in that omega n there, and it would look like with of course some integer n. And we would have like it would be like e to the I omega t, like a normal oscillating function. Okay, so the spacing between neighboring frequencies is 2 pi over t, right? Because we're just scaling by n every single time. So what we're going to do is a little bit of a trick. We're going to make the f of t sum look more like an integral. And integral, we're going to define the following. So define f hat evaluated at omega n times delta omega. Well, we just wrote down this thing is delta omega. That spacing is, we're gonna define that as Cn. So or we're gonna rewrite Cn in that way. So we have this way of calculating these. If we multiply that by t and divide by delta pi, or by 2 pi, then we will get this new thing that we're defining, which is f hat of omega n. Okay, and like I said, we're just doing this to make the sum look more like an integral. So now the sum f of t looks like this. It's a sum from n equals minus infinity to infinity of f hat of evaluated omega n e to the I omega nt times delta omega. Okay? So, if you guys have ever seen a Riemann sum, I don't think that the students had seen that before because it's not, well, actually, no. I mean, I'm sure that when you first learned about integrals, you talked about Riemann sums, but that's what this looks like. This looks like a Riemann sum. And I'll draw that really briefly. This looks like a Riemann sum over omega for f hat of omega e to the I omega t. So like what I mean by that is if we had some sort of function that looked like this, and that function was f hat of omega e to the I omega t, then we're basically taking the value at a certain integer, so like omega 1, we're going up here, and then we're multiplying that by delta omega, the width over here, and then adding that to the sum. and then this is like omega 2. We're going to figure out what the value is there, and then do another horizontal block, and then omega 3 over here, horizontal block, and so on the omega axis. Okay, and then these guys become the area that we sum up. And then of course, if you sent delta omega to be a smaller and smaller value, you'd be approximating the integral area under the curve more and more accurately. Okay, so and that's like the central idea for how you, that's how the integral is actually defined, is that a Riemann sum in the limit of delta omega going to 0 becomes an integral. Okay. And so this is where this is where we're going to make a little bit of a leap. It's still a limit argument. This is actually not super non-rigorous. It's a decently sound mathematical argument. But notice that as delta omega goes to 0, if looking at this expression for delta omega up here that I'm highlighting, that means that capital T, or your period, is going to infinity. Okay? T is going to infinity. And so the set of frequencies that you're summing over, okay, that the omega ends, they're getting closer and closer spaced, and you're still summing over all ends. So you're still summing over from, infinitely small frequencies, or not small, but infinitely negative frequencies and infinitely positive frequencies, but they're getting closer and closer spaced. And so this is the set of frequencies that you're summing over begins to look more and more just like the real axis, like the real line. Frequencies is starting to look like the real axis, which I'll just write as R. Okay? And what I mean by that is that the limit as t goes to 0 of the sum of n equals negative infinity to infinity of f hat of omega, f hat, not f prime, f hat of omega n e to the I omega n t delta w is equal to the integral from negative infinity to infinity of f hat omega e to the I omega t, where omega is now like a continuous value, and that thing is equal to f of t. Okay, and then this thing that has resulted as we took this limit and made the frequencies that we were summing over smaller and smaller and smaller, or sorry, closer and closer and closer together. That is the Fourier transform of f of t. So this is the Fourier transform of f of t. Okay, so the Fourier transform comes from this jump from the discrete representation of a function in a defined period to expanding that period to be infinitely wide, taking up the entire real axis of a variation of the function and integrating over that. Okay? And so, last thing that we'll cover and talk about here is, how do we calculate this Fourier transform, right? F hat of omega. So really what we do is that we are just looking at we can construct this by looking at the formula for Cn, okay? Because that, remember, f hat omega n, the discrete version of this thing that eventually became the Fourier transform, was really just Cn scaled by delta omega, I should say. Okay, so recall that f of t in the Fourier series world is an expansion of the periodic extension of f. So the interval is repeated for all t. So this is a bit of a, again, sorry that this is such a mathematically flavored lecture, but I promise that the stuff afterwards is cool enough that it's worth going through this. So recall that f of t written in the Fourier series representation, which is the sum from n equals minus infinity to infinity of Cn e to the I 2 pi n t over t, is an expansion series expansion of the periodic extension of f. So the 0 to t interval repeats, like I drew before, right? On that basis, we make this argument. Sorry for the yawn. That the integral from 0 to t of f of t dt is the same as the integral from negative t over 2 to t over 2 of f of t dt. Okay, that's just a fact, and that's because the period or the space between negative t over 2 and 0 is the same as the space between t over 2 and t, right? Because it's repeated every t period t block of the function. If I scroll back up here to the very beginning, if like this is, let's do this like this way. So if this is t over 2, you can see that and this is minus t over 2. You can see that t over 2 to t is the same as minus t over 2 to 0. Okay, so we can shift the integration window with impunity that way. So that allows us to shift the integration window for Cn as well. So Cn is normally defined as 1 over t, integral from 0 to t of f of t times e to the minus 2 pi I n t over t dt. We can write that as 1 over t integral from negative t over 2 f of t e to the minus 2 pi I n t over t dt. Okay, and then we rewrite this and bring in f hat into the mix. So remember, Cn is equal to f hat over omega n times delta omega, which is equal to f hat of omega n times 2 pi over t. That was the definition of delta omega. And that's going to be equal to 1 over t times the integral from negative t over 2 to t over 2 times f of t e to the minus 2 pi I n t over t dt. Okay, those 1 over t's are going to cancel. And then we take the limit as t goes to infinity, like we did when we went to got the previous when we got the Fourier series representation of omega, or sorry, Fourier transform representation of f of t, and then this turns into f hat of omega being equal to 1 over 2 pi. Right, we moved that 2 pi over to the other side, times the integral from negative infinity to infinity of f of t times e to the minus I omega t dt. Okay, and that's the formula for the Fourier transform. Okay, so apologies for getting super mathy on you there, but I'm hoping that at least a little bit of that kind of sticks to your rib a little bit, and in the next time you see Fourier series, you kind of understand what's going on under the hood a little bit in terms of what we mean by orthogonality and what kind of structure the Fourier transform idea is built on. Okay, so now what we're going to do is we're going to go ahead and play with a bunch of Fourier series stuff. So I have this this notebook. I'm not going to actually do any sort of live coding here. I'm just going to show you a bunch of plots. So let's see what this guy is doing. Ah, yes. So this is really where you can see what I mean by periodic extension. So this blue line is the function that we're approximating, okay? And with 20 terms in the, so this is a Fourier series approximation where we're truncating at 20 terms in the Fourier series. And with those 20 terms, that you can see it lies right on top of the function very well, and then of course it's going to repeat every one. So here t is equal to 1. If I use a smaller number of terms, so let's see if I have a easy spot to change that. Yeah, here we go. So let's do like 5 terms. If we do 5 terms, you can see that the approximation, it's still qualitatively good, but you're carrying some rather large error where the function peaks and also some phase delay over on the right hand side even here. But that gives you an idea of the idea that the fact that the Fourier series is giving you an approximation of the periodic extension of a function. Okay, and then I think here I wanted to show you what the Fourier transform of different function shapes look like. So this is very important and fundamental to signal processing. So like the box or square pulse in the Fourier domain is what's called a sinc function. So one of the main ways the Fourier transform is used is in signal processing and filtering. So we talked about really what the Fourier transform is sort of doing is it's telling you how much of the power or content of a frequency belongs to each of a signal belongs to each frequency. So like if you have a sound wave and it's like mainly at 40 hertz, but then it has some sort of small oscillation on top of that. If you take the Fourier transform of that, you're going to see 2 peaks, one at 40 hertz and one at the small oscillation. And it also gives you an idea of the amount of power that's contained in those 2 frequency components. And so what people will do often is they want to take the function, apply the Fourier transform to bring it into frequency space, and then they want to apply a filter and like multiply all the components that are really high that are causing the noisiness and knock them down to 0. But if you use a sharp filter edge, like a box function like this, when you try to invert back to real space, you can actually bring in some features that you don't actually want. Okay, so like there's a whole. I mean, this is a whole deep rabbit hole. Very. There's whole courses and sequences of courses that can be taught on the Fourier transform. So I won't try to really go super deep into it here, but these are some important things. So the box function looks like what's called a sinc, and then you also have the Gaussian. A Fourier transform of a Gaussian is a Gaussian, so that's an interesting fact to know. And then you also, this is just kind of an example, right? So here's this weird function. You have some oscillations here. The broad variation of the function is kind of slow. And so that's why you have this big peak at a frequency equal to 0, but this lobe out here at a frequency of 5, it has to do with this oscillation that's that's obviously a big part of the function as well. Okay. Let's see what's going on here in this one. Yeah, so this is an idea of filtering, right? So, like I was just saying, what you can do, so you have this original signal, right? And then there's a noisy version of the signal. And so what you can do is you can, the original Fourier series representation looks like this. It's these nice, it has 3 frequency components that are very clearly visible, okay? And then if you add a bunch of noise to that signal, like this might be what you actually measured, right? It has to do with noise, to various factors that have to do with your instrumentation or whatever. This looks like a very mangled version of this clean signal, right? Well, if I take the Fourier series representation of this guy, and then I apply a filter to it where I knock out all of the high frequency noise that's happening between, roughly 45 hertz and 100. I just knock all of that down, and then I take the inverse Fourier transform of that. I get the orange signal, which is kind of like a almost perfect clean reproduction of the original signals, right? It's almost right on top of it. There's some error, but it's a lot cleaner and closer to what you are seeing here as opposed to this, right? It's like a big improvement from this mess to there, right? But that's like one of the ways you can use the Fourier transform. Okay, and then let's see. This is actually a pretty intricate idea. We don't necessarily need to talk about this. You have to be very careful when sampling, and you can prove that using the Fourier transform, but we won't talk about that here. Yeah, and this is another thing about downsampling. So, if you downsample, so like imagine you have a signal that has 1,000 time steps per second, and then you want to move from that to 10 time steps per second for some reason. Okay, if you just grab the every 10th step, that is like that. What that does is it causes it messes up your Fourier domain, and you bring in these frequency components. So like at the original high rate, this is your very clean Fourier spectrum. You have 3 clear frequency components in this signal. And then if you just do a naive downsampling procedure, then you have your first 2 components, yes, they're clear, but then you have this new component at 20 that didn't exist before, that's been folded into your frequency band, that is corrupting your signal, okay? Corrupting your representation of the signal. And you can do a special kind of downsampling to get you to the same frequency that uses filtering before you downsample. And that allows you to eliminate that extra node of frequency information that really shouldn't be there, and you just get the first 2 original frequencies. Okay, that's another sort of honestly pretty intricate point for this lecture, not very important. Okay, so I think this is where I wanted to show you something. I think this cell actually takes a while to run. Should have run it while I was talking about the previous cell. But yeah, suffice it to say that if you ever get into signal processing, or one thing that I worked on over that I often encounter when I'm processing physics data for one deep learning project or another where I'm working with physics data. I have to be very careful with how I downsample and upsample the data. Not only do you need things to be causal, but you need to make sure that you're not bringing in any sort of aliasing by doing it in a naive way. Okay. Another thing that you can do with the Fourier transform is you can actually create like edge maps, right? So you can do Fourier transforms over 2 dimensions, and that's what this looks like here. Like this is the original image that I took in I think it was in the Piazza del Popolo in Rome, and I took the Fourier series, 2D Fourier series of that, and that looks like this image here. And what I did was I essentially I zeroed out all of the stuff that's um, around zero frequency. So like all of the parts in the image where nothing is changing from pixel to pixel, basically, right? And then so I applied that filter, and then I did the inverse FFT, and what you end up with is an edge map, right? It tells you wherever there are pixels that are neighboring each other that are very different from one another. Like there's a high frequency of variation in the pixel values, and so you end up with an edge map. So that's another thing where you can use a Fourier transform is to map the edges and images. Okay, and then there's this other thing that is actually from an interesting homework assignment that I got in one of my classes at Stanford. So there was this image of Stanford's campus. This is near the Oval at the front, taking a picture of Hoover Tower, and it's actually that they had taken the Fourier transform of this image, and then they embedded a digital watermark, okay, in the image, and then did the inverse Fourier transform again to get this image out. So this image has a hidden watermark in it that you can't actually see in the actual image, right? But if you analyze it using Fourier transform methods in a very specific way, you could back out that there's this hidden portrait of Fourier in the image. And then the last part of the assignment was to say run the algorithm again on the image that you revealed, and when you do that, you found Waldo. So the Waldo image was the hidden watermark in the first hidden image, which was the hidden watermark in the photo of Stanford's campus. So I thought that was kind of funny. I wanted to share that in this lecture, but just as an illustration of the kind of things you can do with the Fourier transform. When you invert something into frequency domain, you can do some things there, and sort of hide things, both in audio and in images like this, right? Like I said, apologies. This lecture is, I don't think none of the stuff that you learn in this lecture is actually going to live in or be tested or on an exam or something, at least not for the foreseeable future, until maybe I find a way to incorporate these Fourier ideas into other parts of the class or shift things around, make this a little bit more palatable for engineering students. But I still think that it's a topic that you should probably be exposed to at least once. Even though you're not electrical engineering students or something, where Fourier transforms, or I think maybe electrical engineering students think about Laplace transforms a bit more, but in any event, signal processing, anybody who's doing any signal processing will think a lot about Fourier transforms. But for the rest of you, I still think it's important, and I'm grateful that you sat through the lecture up to this point. But for now, I'm going to call it for the day, and for the last lecture we'll just be doing a review, and that'll be it for the class. So thank you very much for listening, and I'll see you next time for the final recorded lecture of this class.